Okay, 6.2, applying the slicing method. In this video, our objective is to apply the slicing method to find the volume of an arbitrary solid of revolution. So here we're going to extend the concept of the disk and washer methods to revolution about a y-axis or an arbitrary axis. And that will involve a few different techniques that we'll apply. So this is mostly example driven. So we'll use the examples to drive our new insights about extending this method. And first we'll do an example where we have a disk method application and we're revolving about the y-axis. So here, the region that we're rotating is bounded by y equals 1 over x, y equals 1, and y equals 3. And we're rotating this about the y-axis. So axis, the y-axis. So each one of these has an axis of revolution, and here what we're doing then is we're going to be looking at, I'm going to try to make the graphs a little bit bigger, just so that we have a much better picture. So let's see. Call that 1, 2, 3. Oh, let's make that bigger then. Let's just extend this so that, let's say 1, 2, 3. Okay, that should be better. Then our curve is going to look like this, roughly. Okay, so that's our y equals 1 over x. And y equals 1. Sorry, that's y equals 3. And y equals 1 is here. Okay. So the region bounded between those two curves, okay, and we're rotating that about the y-axis. So it should look something like this, okay? So we get a mirror image there. And since we're rotating about this axis, it should look something like this. Kind of like a funny cone shape, okay? All right, but when we rotate about the y-axis, we can't apply the slicing method, or no, we couldn't apply the slicing method by doing the integration with respect to x. What in fact we need to do is we need to take a horizontal slice like this, and recognize that that is going to be rotated about the y-axis. So that's going to make a horizontal disk there, okay? Which means that we're going to need to express everything in terms of y. Okay, so that means y equals 1 over x. We'll convert that into x equals 1 over y, which is not that bad. Okay, and then our limits of integration will be between the two y values. So for y, between 1 and 3. That's not too bad, again. What this means then is that we need to change our definition of how we calculate volume based on an integration with respect to y. So that'll be, sorry, I'm going to change that to c and d. Integral from c to d of pi f of y squared dy. Because this is still the disk method, so there's no gap in between, so we can just go ahead and use f of y as the radius of that disk. And so in this case, that will become the integral from 1 to 3 of pi times 1 over y squared dy. Pull out the pi, integral from 1 to 3, 1 over y squared dy. This will be pi times negative 1 over y from 1 to 3. So I'll continue that calculation over here. Pi times negative 1/3 plus 1, and that turns into 2 pi over 3. That's our answer. Okay, so the key insight here is specifically that we need to convert first into an expression where we're integrating with respect to y. And we can do this again by applying the washer method. So in the next example, let's see this with the washer method example. Revolution about the y-axis again. And here our region is going to be, we're going to rotate the region bounded by x equals 2 minus y, x equals 1 minus y, for y between 0 and 1. And then again, we said the axis is the y-axis. So we're going to find the volume of the solid generated by rotating this region about the y-axis. All right, so another picture. Here is that. Okay, so I have here two lines. Okay, both of them have a negative slope. One crosses the y-axis at, the x-axis at 2. The other one crosses the x-axis at 1. Okay, so it should look like this. Here's 1. Here's 2, 2, 3. One of them should look like this. The other one should look like this. Okay. So the region here, in between those two, are what we're going to focus on. So the rotation about the y-axis means we get something that looks roughly like that. So it is going to open up with a gap here. The problem is, if you notice, we actually end up with two integrals. And the reason for that is there are two distinct regions here. One where, or I'm sorry, I did this wrong, didn't I? Oh, okay, I'm going to have to scrub that. That's not the right picture. Start over. That's not the right picture. Sorry. Okay. There's that. There's that. Okay. 1, 2, 1, 2. Okay. Let's start over. 1 minus y is the same as, so remember that if this is the y-axis and this is the x-axis, we can rewrite each one if we want to in terms of the function as a function of x, just so that we know how to graph it but it's not strictly speaking necessary. But it might help. But basically, the idea here is that they're going to have the same slope, but different y, intercepts. And in fact, I'm going to, because this needs to be between 0 and 1, I'm going to make that 1. Okay. So the first, no, let's not do that. Jeez. Why would I do that? 1 and 2. Okay. Then the first line starts at 1 and goes down by 1. And the second line starts at 2 and goes down by 1. Okay, now that's right. That's right. Okay. So then if we are setting up the integral here, notice that we're going to have to split it into 2. Why? So when we're rotating about the y-axis, remember that what's actually happening here then is you get something like this, and it's going to form a cylinder shape of sorts with the middle bored out. I'm not going to draw all that because I want to make this picture as clear as possible. Namely, when I draw in my infinitesimal slices, okay, that are going to make my rings, I actually get 2 cases here, okay, because I'm actually looking at 2 distinct pairs of curves, okay. So let's call this volume calculation 1, so V1 and V2. So for volume calculation 1, the upper curve is that line that we talked about, the x equals 2 minus y, and the lower curve is actually the y-axis, so x equals 0. So this one is actually going to be, this piece is just straight up disk method. For V2, oh, and of course the limits of integration, y is going to be between 1 and 2. For the second piece, our upper curve is now this dotted black line, which is x equals 1. And the lower curve is now the other line, which is 1 minus y. And for that, we have y between 0 and 1. All right. Then, notice that for this one's just straight up disk method. But this one's a washer method about the y-axis, okay? So when we do this calculation, we're going to split it up into V1 and V2. Which is going to be V1 is just the integral from 1 to 2 of pi 2 minus y squared dy plus the integral from 0 to 1 of pi times 1 squared minus 1 minus y squared. Oh, it's subtle. See? So this one is the washer method where we have the upper curve squared minus the lower curve squared. And that does matter. This is important to split it up into the 2 volumes, otherwise we're not doing this correctly. But from here, it's not too bad. Now we're just integrating. And I don't want to say that as we're just integrating. What I mean is, at this point, it's more about the algebra of the problem rather than the geometry of the problem. So the integral from 1 to 2 of 4 minus 4y plus y squared dy plus pi integral from 0 to 1 of 1 minus 1 plus 2y minus y squared. And then if I clean this up a little bit, this ends up being the integral 4 minus 4y plus y squared. That one's fine. dy plus pi, the integral from 0 to 1 of 2y minus y squared dy. Okay, and now if you follow along with me, we'll finish up these calculations. But we're going to end up with equals pi times 4y minus 4y squared over 2 plus y cubed over 3. I'll just make sure that I did that right. I'll go back to my last page. That looks right. From 1 to 2 plus pi, and if it was 2y, then that becomes y squared, and then minus y cubed over 3 from 0 to 1. Okay. This is horrible, but it's fine. We need to get used to these sorts of calculations because they're going to come up a lot. All right? So first things first, plug in 2 to the first expression. So that's going to be 8 minus 8 plus 8 cubed minus pi 4 minus 2 plus 1/3 plus pi. Now I'm plugging in 1 into the next. I'm using FTC2 twice, basically. Right, so 1 squared is 1 minus 1/3 minus pi, and then that's going to end up being 0. So there's no need to actually write all this out. But I just wanted to illustrate that. Okay, the first term, or the first set of parentheses, reduces to 8 pi over 3. The second one will become 2 plus 1/3, which is 7/3. No, yes. Minus 7 pi over 3 plus 2 pi over 3. And then the last one was 0, so that one doesn't even count. So that's going to be 8 pi minus 7 pi plus 2 pi all over 3. And that should be 3 pi over 3, or pi. Wow, wasn't that nice? I love it when things end like that. It makes it really fun, too, because it's all equality. So you can say, what's the definition of pi? Duh. It's just the volume of the region of the solid generated by rotating the region bounded by x equals 2 minus y, x equals 1 minus y, between 0 and 1, rotated about the y-axis. So easy. I'm being sarcastic if you can't tell. But the general ideas apply here regardless. So let's finish off. No, we still have 2 more examples here to work with, because now we're going to be talking about what happens when we use an arbitrary axis that's parallel to the x-axis. Okay, so new example. Oops, I always do that. Example. So in this case, we're revolving about an axis parallel to the x-axis. Okay, so revolution and I know that that technically could include the x-axis itself, but we're talking about some other axis. Okay, so let's write out the problem. So find the volume of the solid generated by, these problems can be kind of wordy. The region bounded by y equals sine of x, y equals cosine of x, x between 0 and pi over 4, about y equals negative 1. Okay. Oh, and about y equals negative 1. So that already covers the axis of rotation. I'm going to draw it in excruciating detail here, and then on the next page, I'll set up the integral, okay? So roughly what we're looking at here is we're looking at something like this. Okay, so remember that we're looking at just between 0 and pi over 4 for the x-axis. So if we imagine that this is like pi over 2 right here, this is pi over 4, and here's 1. So what does sine of x look like? So sine of x is on its way to reaching its peak at pi over 2. So sine has a local maximum at pi over 2. It should look something like it's going up like this. Hasn't quite reached the apex of its trajectory. And then cosine, on the other hand, is doing the opposite. It is coming down from 1 and is going to be crossing the x-axis at pi over 2. So you can imagine that they kind of go like this. So we're halfway on that journey. And the line that we're rotating this about is the line y equals negative 1. So our rotation is happening about this line. And if you can imagine that it actually is coming down like this. Sorry, I know this isn't the greatest picture. So this region here that's what's being rotated about. Okay, let me erase that because that's going to get too cluttered. No. Okay, I'll fix that. All right. So how do we actually set this up if we want to use the slicing method? So what we're actually using here is this is our infinitesimal slice, and of course it's going to be swept out all the way down here, et cetera, right? It's going to get closer and closer to and then come back around. I'm not known for my artistic ability. Okay, so here's the question then. This is an annulus. This is the washer method, okay? So washer method. And for rotating about this line, y equals negative 1, then to figure out the inner radius and the outer radius, so outer radius, we're actually looking at the distance between the upper curve and the line y equals negative 1. So that's going to be f of x minus negative 1, which is f of x plus 1. Okay. And similarly, for the inner radius, the same distance, but between the lower curve and the line y equals -1. So that's actually going to be g of x minus -1, which is g of x plus 1. Okay. All of this is to say that the infinitesimal slice now, okay, thin slice, if we're looking at our dv calculation here, right, in the most general aspect here, we're looking at pi capital R squared minus little r squared times dx. But capital R squared and little r squared depend on the distance to the axis of rotation, and we already factored that in the last slide, or last page, sorry, where we did this calculation here and here, okay? So then assuming we can call the axis, the line y equals c, little c, lowercase c, the calculation actually is going to be the integral from a to b, those are the bounds for x, of pi of the upper curve minus c squared minus the lower curve minus c squared dx. Wow, right? This complicates it quite a bit. Like there's layers to this, right? Namely, this is the outer radius, this is the inner radius. And in our specific example here, we're looking at the integral from 0 to pi over 4 of pi times cosine of x plus 1 squared minus sine of x plus 1 squared dx. Wow. Okay, so we're going to use some things with trig functions right now that will be helpful later on as well. We do have a section entirely focused on working with integrals of trigonometric functions, but here we're going to start seeing some of that stuff show up. Okay, so a really important note here, you're going to want you to have your trig identities handy. Okay, if you don't know them well, just pull them out. And eventually, as you work with these, you'll get really comfortable with them. All right, so let's simplify what's going on inside the brackets. So it's the integral from 0 to pi over 4 of pi bracket cosine squared x plus 2 cosine x plus 1 minus sine squared x plus 2 sine x plus 1 close bracket dx. Okay. Some of this is not going to be too hard, but whenever you see cosine squared and sine squared, you're going to want to see if you can apply a trig identity. Namely, here, if we put those two together, what we've got here is cosine squared x minus sine squared x plus 2 cosine x plus 2 sine x, and then the ones cancel. And we know, or we can verify very quickly, that cosine x minus sine squared x, sorry, cosine squared minus sine squared is the same as cosine of 2x. So this will simplify nicely to 0 to 2 pi over 2 of pi times cosine 2x plus 2 cosine x plus 2 sine x dx. And here we can use a little the substitution rule. So the integral of cosine of 2x, if we let u equals 2x, then du will be 2 dx, which means when we split that off, right, the integral of cosine 2x dx will turn into the integral of 1/2 cosine u du, and that'll be 1/2 sine of u plus c, although that part won't matter to us, equals 1/2 sine of 2x. Okay, so when we go to integrate that, that's the antiderivative, and we don't have to worry too much about that now. So all right, so let's finish up this integral. So it equals pi times, remember we said that was 1/2 sine of 2x, and then was that a minus or a plus? That was a plus. It's all addition at this point. Plus 2 sine of x minus 2 cosine of x. These are the integrals of those two remaining terms, and it's all from 0 to pi over 4. Okay, so there's a lot here. We're going to split this up based on pi over 4 and 0. So we got pi of 1/2 sine of 2 times pi over 4 is just pi over 2, plus 2 sine of pi over 4, minus 2 cosine of pi over 4. Here's where you really are going to want to know your unit circle, because very quickly you can see that even if, it doesn't take that long to look these up, you're really going to want to be quick with these because there's going to be so many of these calculations, okay? So let's just go through them real quick. Sine of pi over 2, where the pi over 2 is right on that, the y-axis, so that equals 1. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2 also, because that, remember that that's that angle where they equal each other. Sine of 0, 0. Sine of 0, 0. Cosine of 0 is 1. Okay, now we replace everything. So that's going to be pi times 1/2 plus, and then root 2 over 2 times 2 is root 2. Minus 2 times root 2 over 2, which is root 2. Minus pi times negative 2. Okay, we're almost there. We're almost at the end. What this means then is these will cancel out, and that means we're left with 1/2 pi plus 2 pi, which is 5/2 pi. And that's our answer. Okay. So it's a lot. The setup, right, was actually maybe not the worst part of this whole transaction. Let's just do one more example. And in this example, we're going to do basically the equivalent of this, but where we're rotating about an axis parallel to the y-axis, okay? All right, then, what's our region? What we're going to look at is it's bounded by y equals x squared, the y-axis, and y equals 2. About the line x equals 3. So let's draw this. Okay. So here's 1, here's 2, here's 3. This is the axis of rotation, so I'm going to fill that in right now. 1 and 2. Okay, so between y equals 2, so we have y equals x squared. That's not too bad. What am I doing here? Oh, I'm going to have to edit this. Damn it. Okay. Okay, so y equals x squared, that's the standard parabola. And if we're going up to 2, then it looks like we'll be going like this. Something like that. And that is our region actually right there, okay? Which means our infinitesimally thin slice is something like this, okay? But with respect to this axis, right? Whoops. With respect to this axis, that means we're actually going to be taking this and mirroring it over on this side. So it'll look something like this. So I'll just extend this line here. And you'll see that on the other side, you'll find the image of that that infinitesimally thin slice. All right, so then same thing, annulus, which means what is actually the thing that we're integrating. So inner radius and outer radius. The upper curve is this line. So the upper curve here is x equals 0. That means r in this case, capital R, is going to be the distance between 0 and 3. So 3. And actually that should be positive, so I'm just gonna make that 3. And little r was that right? No, that's right. Little r then is going to be the difference between 3 and this line right here. So that's going to be 3 minus x squared. And it's 3 minus x squared because when you're looking at it, you really want to be looking at it in terms of the x-axis becomes your y-axis, sort of. So the axis of rotation is actually above your region that you're rotating. And so what we end up with is our dv is going to be pi times 3 squared minus 3 minus, oh, and of course we have to write this in terms of y, so hang on, pause. If we're going to be writing it in terms of y, so it's going to be x equals square root of y. Yeah, okay, here we go. Then we have 3 minus square root of y squared dy, and that is the washer, infinitely thin washer that we're actually going to draw out. Okay, then on the next page we'll actually do the calculation. So the volume is going to be the integral from, what are our limits of integration? So what is what does y range between? We're looking at between 0 and 2 of pi 9 minus 3 minus root y squared dy. And from here, it shouldn't be too bad. So when we set this up, we're gonna, okay, let's simplify the inside here. From 0 to 2, pi times 9 minus 9 minus 6 root y plus y dy. And so we'll end up with the integral from 0 to 2 of pi. 9 minus 9, those cancel out, so we're just going to get 6 squared y minus y dy minus y. Yes, minus y. Yeah. And then we integrate that, so it's going to be pi times, remember that's y to the 1/2. So when you integrate that, you're going to have a 3/2 in the denominator, and y raised to the 3/2. 0 to 2. It's going to be pi 6 times 2/3 y to the 3/2 minus y squared over 2 from 0 to 2. It's going to be pi of 6 times 2/3 is 4. So 4 times 2 to the 3/2 minus 2 squared over 2 is 2. And then the minus pi times 0 because the whole thing becomes 0 when you plug in 0. Then this means that we have 2 raised to the 3/2 power is going to be, let's actually calculate that. So that's one way of thinking about it is 3/2 is 2 to the 1 times 1/2, so plus 1/2, sorry, which is the same as 2 times square root of 2. Okay, then that means the 2 and the 4 will combine, and that'll make 8 pi root 2. Or 8 root 2 pi if you want, if you prefer. That's probably better math manners to do it that way. That's our answer. Okay. So in this case, the calculation itself wasn't too bad. In this case, the setup was a little bit more involved, okay? But the important part is always to think about, okay, what is the inner radius, what is the outer radius? Remember that they're getting squared, so it doesn't, these are meant to be positive values, okay? And the infinitesimal then isn't fundamentally too different